Now we are recording.
Okay, perfect. So this is just going to be this last lecture. This is the last lecture on the first chapter of preliminaries. It's just going to be an overview on representation theory, weights, and so on. So let's start by the basic definitions. Let G be a Lie algebra over either the real numbers or the complex numbers. So we will say that a representation of G in a finite dimensional vector space over the same base field which we call V, is simply a Lie algebra homomorphism rho from G to the Lie algebra GL of V, which I recall that the Lie algebra GLV is simply the set of all the homomorphisms with the commutator operation. So we also say that V is a G module, and there is a notion of equivalence between representations in the sense that two representations are equivalent if they are the same vector space and the Lie algebra acts on the same way. So to be more formal, we say that two representations rho from G to GLV and rho prime from G to GL V prime are equivalent or isomorphic if there exists an isomorphism, a vector space an isomorphism F from B to B prime such that F of rho of X, oh, this is badly written, such that F rho X, the composition of F and rho of X, is the same as rho prime of X times F for all elements in the Lie algebra. Okay? And we will write that rho is equivalent to rho prime with the following tilde sign. So in terms of a diagram, what we will have is that given any element of the Lie algebra, we have the element of the Lie algebra induces a linear transformation of V, rho of X, and it also induces another linear transformation on the space V prime, which is rho prime of X. So the isomorphism condition simply means that if we plug here our vector space isomorphism F, then this diagram is commutative. Okay. And the most important example of an isomorphism between representations is taking any linear representation of transformations over a vector space and converting it into a matrix representation by choosing coordinates. And this is what we understand as the matrix form. So fix a basis, which we will write by calligraphic B. Then any representation of G over B can be thought as its matrix form. Its matrix form, which I'll write by rho bar, going from G to the Lie algebra of matrices GL N, okay? Where N is simply the, I put the base field somewhere, GL N K, where N is the dimension of D. So how do we do this? We simply take rho bar of X to be the matrix of this linear transformation rho of X relative to the basis B. And it is very easy to see that this representation rho bar is equivalent to rho by simply taking the isomorphism, which takes the canonical basis of Kn into the chosen basis B of B. And finally, another construction that we can make, apart from the matrix form of a representation, is the dual representation, okay? So this is one example, and also, sorry, the dual representation of a representation rho will be a representation over the dual space of V, which we write as rho super V, going from G to the set of linear endomorphisms of the dual space V star. And how do we define it? Well, the elements of V star are linear forms, so if we want to describe how the transformation rho V of X acts on the linear form, we need to know how this new linear form acts on vectors. And we define the action on its vectors to be minus lambda of rho of X V. Okay? We can also say, in other words, that the dual representation is simply the negative transpose of the original representation. Okay? And now we're going to talk about the decomposition of a Lie algebra representation over invariant subspaces and and the matters of reducibility, irreducibility, and complete irreducibility. So essentially, invariant subspaces of a representation are those that remain invariant under the action of the Lie algebra. So in that case, we can restrict the representation to any of those invariant subspaces. So we say that a subspace W of B is invariant if every transformation of the representation takes W to itself. So if rho of X of W is contained in W for all X in G. And as I said before, this allows us to restrict the representation of the whole space into a representation of the subspace W because of this condition. We get a sub-representation which we denote as a restriction, that is rho restricted to W, taking G to GLW, simply defined by the following formula. It's simply the natural definition of the restriction. Okay? And it may be possible that in some cases these invariant subspaces can reconstruct the whole representation, and that's what we call a sum of representations. Assume then that V is a sum of invariant subspaces and okay, so since it's the sum of invariant subspaces, we can define the restrictions, which we denote simply by rho sub I. Okay. So in this sense, we will say that rho is the sum of the invariant subrepresentations. That rho is the sum of the rho I. And we denote it simply by rho equals sum from 1 to R to the rho sub I. And the matter of reducibility and irreducibility and complete reducibility is simply defined by the behavior of these invariant subspaces, if there exist invariant subspaces or not, and also if invariant subspaces admit complementary subspaces. So it's like a generalization of the definition of a reductive Lie algebra. So we say that a representation rho is irreducible if it has, quote unquote, no invariant subspaces. I say quote unquote because the zero space and the total space are always invariant. So the irreducibility condition means that there are no more invariant subspaces. So if it's only invariant subspaces, are the null space and the total space. And we will say that it is reducible otherwise. Rho is reducible. Okay. And on the other hand, we will say that rho is completely reducible if given any invariant subspace W of V, there exists another invariant subspace which is complementary to W. There exists, I don't know, so W prime, another invariant W prime such that V decomposes as the sum of the invariant subspaces. So notice that irreducible representations are by definition completely irreducible. Okay, so maybe it seems a little contradictory, but but yeah, so these two concepts are opposite, and irreducibility implies complete reducibility. But and also irreducible are completely reducible, but also the sum of irreducible representations is always completely reducible. And in reality, these two concepts are equivalent. This is another fact which says that if rho is completely reducible, then we can find a decomposition of our space V into invariant subspaces in which the restrictions are reducible. And it's an equivalence. Only if rho is the sum of some irreducible representations. And also the decomposition is unique up to isomorphism. The composition is unique up to isomorphism. And well, we say that the rho sub I are the components. So these are the irreducible components. Okay. So for example, we saw in the first lecture, if I recall correctly, the definition of these reductive Lie algebras. If you notice, maybe you noticed that the reductive Lie algebras are precisely those for which the adjoint representation is completely reducible. Okay. So just to have an example in mind. So where's the eraser? Okay. Now we're going to talk about the weights of a representation, which are very similar, are like a generalization of the root systems, and in some ways they behave similarly. So, and also before I forget, a small condition that implies reducibility is that in the semi-simple case, representations are always completely reducible. Okay? So this is another fact which says that if G is semi-simple, then every representation of G is completely reducible. Okay. Where's this? Okay. So now let's come back to the complex semi-simple case in which we talked about roots. We talk about roots, maximal Taurel subalgebras. and we introduce the weight space decomposition. So assume that G is from now on a complex semisimple Lie algebra. So if you remember, given any complex semisimple Lie algebra, we we know that the commutator of G with itself is equal to the whole space again. So if we apply the representation to both sides of the equation, then the elements of the representation are also elements of the commutator. Okay, but this image is contained in the bracket of the Lie algebra of all endomorphisms, which we already saw that is the set of all linear endomorphisms that have trace 0. So keep in mind that if we have a complex semisimple Lie algebra, all the endomorphisms associated to a representation must have trace 0 because of this observation. Okay, so I'm just going to state the weight space decomposition theorem. So it is stated as a fact. And it's the following. Given any representation of the complex semisimple Lie algebra, we have a weight space decomposition defined as follows. So V is going to be equal to the sum of some spaces V lambda, where lambda are elements of the dual space, defined as follows. So they are in this set phi of rho is given by sorry, I wrote this. Yeah. No. Sorry, small mistake. There isn't a definition for this, just the definition is for V lambda. So sorry, I'll state everything again in a moment. V lambda such that rho of H V is equal to lambda H V for all H. Okay, so what I wanted to say is that if we have a representation of a complex semisimple Lie algebra over a vector space V, then as we did with the adjoint representation, we can think of the common eigenspaces of the representation, which are defined as this V lambda, given any real form, any linear form lambda. We say that V lambda is the set of all vectors that are eigenvectors for all transformations of any maximal Tarasov algebra. Okay, with eigenvalue, the value of the linear form in the elements. Okay, see, maximal Tarasov algebra. So this should remind you of the roots in the case of the adjoint representation. And V is the sum of the common eigenspaces. And this phi rho is the set of all of all V lambdas, which are of all lambdas, such that V lambda isn't 0. So the first example is in the case that rho is a joint representation. In this case, the phi of rho is equal to the 0 vector, which we distinguished. Remember that the eigenspace was here the maximal total subalgebra, to which we join the set delta of all roots. So if you remember, the roots were exactly this for the adjoint representation. Also, the set of weights for the dual representation is equal to minus the system of weights for the original representation. Okay? I'm going to state now some formulas that hold for these weights that are also very similar to what we saw in the complex semi-simple the algebra decomposition. So remember that we introduced in the last section some SL2 systems, H alpha, E alpha, F alpha, which we are going to use again. We know that lambda of H alpha, we computed these in earlier sessions. And so it's equal to the following quantity. And this is always an integer. Okay? When first lambda is a weight and alpha is a root. Okay? On the other hand, remember that we had that the bracket of root spaces is contained in the root space of the sum. Here, what we have is that rho of E alpha over V lambda is contained in V lambda mass alpha, which is like a weaker condition. Again, whenever lambda is a weight, we put it here, and alpha is a root. And also, if we have an automorphism of G such that theta preserves the maximal total subalgebra, then one can check that the weight system for the composition of theta with rho is equal to the inverse of the transposed map of theta of the original weight system. And finally, the last thing that I'm going to state now is that the set of weights is invariant by the Weil group. It's invariant by the Weil group. In this case, it would be the construction of the dual version that acts on the dual space. Okay? And now,
I'm sorry, can you hear me?
Yes.
Is the representation V supposed to be finite dimensional, or does it work for like an arbitrary representation?
Yeah, this is always for finite dimensional vector spaces in which the base field is equal to the base field of the Lie algebra.
Okay, great. Thank you.
Okay. Okay. And now we have these highest vectors and highest weights. Perfect. So now let's choose a positive criterion in the roots. And remember that it was equivalent to choosing a Weil chamber, a connected component of the set of regular elements. Okay, so fix a Weil chamber. D. Okay. So this while chamber will induce positive roots, and it will induce, in particular, simple roots with set of simple roots which we usually denoted by capital Pi, and which use these generators of the SL2 systems associated to the root space decomposition and canonical generators. HI, EI, and FI. So we will say that a weight vector that is one of these common eigenvectors, an element of B lambda, a weight vector V is a highest vector if the elements E alpha, sends V to 0 for every alpha, for all alpha positive roots. Remember that positive roots are generated by simple roots, so it's equivalent to saying that rho of EI sends V to 0 for each I. Okay? The weight of V that is the the lambda such that V is in V lambda is called a highest weight. For the representation. Okay? And in the irreducible case, this highest weight is unique. I'm going to keep this the word fact. So in the irreducible case, if rho So I don't know what happened. Can you hear me?
Yeah, now it seems fine.
Yeah, I think it lost connection or something like that. So the last thing I was going to say that irreducible representations have a unique highest weight. I don't know if that's the last thing that you heard from me.
Yeah, pretty much. We lost connection when you moved to the right board.
No, it happened to everyone then. Okay, I thought I was the only one. Okay, okay.
Yeah,
Right.
it was a little strange. Well, at least I wasn't. I wasn't. I said before, we said that a weight vector is a highest vector if the transformations induced by the E alpha send V to 0. And in that case, the weight associated to the vector V is called the highest weight. And these are unique in the irreducible case. So if rho is reducible, then the set of weights has a unique highest weight. I don't know if I put it, yeah. Which we will denote by capital lambda. And the dimension of the associated weight space is 1. So it's simply a straight line. And this highest weight and these highest weights allow us to characterize a representation of an irreducible, representation. 2 irreducible representations are isomorphic if and only if they have the same highest weight. By the way, the recording is still on, right? Yeah. Okay. And remember that completely reducible representations could be written as the sum of irreducible representations, and we're working with semisimple algebras. So every representation is completely reducible. So a more general statement than this is that a representation of G is determined again, we say it up to isomorphism. Well, it's by the system of highest weights of each irreducible component. Right. And now we're going to so these are going to be related to dominant elements. And again, this will characterize our representations. Remember that the weights were always contained in the system of weights is always contained in the real form of the dual of the maximal integrals of algebra. They were real linear combinations of roots. Okay? So an element a lambda of this real form is called dominant if it takes the hi into non-negative numbers for all I. So what is going to be true is that these highest weights are always dominant, and dominant elements are always highest weights of some representation. So these characterize irreducible representations. So I'm going to write it here as a and it's the following fact. Highest weight is always dominant. And conversely, if capital lambda is dominant, such that it takes the hi into integers, I forgot to mention that earlier. We will abbreviate this by saying that lambda I is equal to lambda of hi. Well then, these dominant elements are highest vectors. Sorry, are highest weights. There exists an irreducible representation with highest weight lambda. All right. I think I have space here. Still, I will erase this. Let's go on. So now let's remember that we have a basis for this real form T star of R, sorry, of T of R, which is simply taking the HIs. Okay? We're going to consider its dual space. Its dual basis, sorry. So H1 up to HL, where L is the rank of the semisimple Lie algebra, is a basis of the real form. Okay? So let's take the dual basis. And we will denote it by omega 1 bar up to omega L bar. And we're going to call these dual elements the fundamental weights. We say that the omega I bar are the fundamental weights. So these are clearly dominant, and they have an irreducible representation associated to each one of them, right? So the representations that are going to be associated, that will have these elements as highest weight, we will call them the basic representations. Here. The reducible representations associated to each omega I bar are called basic representations. Notice also that these lambda I for a dominant element are precisely, these lambda I are the coefficients, are the coordinates of a dominant element lambda with respect to the dual basis. That is, if we have, well, any element, but we're going to be interested in dominant elements. If we have any element in the in T star of R, then by linear algebra, lambda is the sum of every lambda I times omega I bar. And lambda I is precisely the value of lambda at hi, because this is a dual basis. Okay? And from this, you can construct a thinking diagram from the representation. Simply, if we so suppose that rho is an irreducible representation, with highest weight lambda. Well, we take the thinking diagram of G. And we will take the nodes corresponding to the representation and we will write over them the coefficients lambda I. And write the, here, where was this? Write the coefficients lambda I over the corresponding vertices of the diagram. The result of this process will be known as the thinking diagram of the representation now instead of the algebra. So the result is the thinking diagram of rho. Okay. So what do we have now? Okay, so now I'm going to introduce some relations involving how the highest weight generates. So we're going to see that the highest vector generates our vector space as a module instead of as a vector space. I'm going to see some identities relating these these generations. Yes. Yes.
There is some relation between the fundamental weights. I mean, some weight is bigger than other one or something like that. This is the first one or the last one.
If there is a bigger one. So I think we could use the positivity criterion, right? In the sense that these are elements of the dual space. So we could, they are, yeah, but these aren't roots in this. I can say now.
Okay.
But maybe it's possible. Maybe by taking the Weil chamber you can do it, but now I'm not sure.
Thanks.
No problem. So let rho be a irreducible representation. And take a highest with highest weight. Lambda. We choose the highest vector. Remember that highest vectors form a one-dimensional subspace. So we call this lowercase v lambda. And this is going to be in the vector subspace v lambda. Well, firstly, v lambda generates G. In the sense that by using the operation of the representation as well as the sum of vectors and scalar multiplication, we recover G by starting with v lambda. And now let's define the following vectors. Which are indexed in the following way. We will say that V sub empty set is V lambda. So we did nothing to V lambda. And on the other hand, we will call V I sub 1 dot I sub k to be the result of applying the following transformation to V lambda. Rho of E I sub 1 up to rho of E sub ik to V lambda. And in principle, we're going to assume that these indices are non-decreasing. So 1 is less or equal to I1. Or sorry, they need not be non-decreasing. They're just between 1 and 0. They could be in any way, shape, or form. Okay. So the fact that V lambda is a generator of V can also be seen as the following. So V lambda generates G as a module, but the vectors V I1 ik generate V as a vector space. I just realized that this wasn't properly written. I said before that V lambda generates V, not G. So it generates a vector space, but as a G module. And now I'm going to write several identities involving these vectors V I sub 1 up to I sub k. Some identities. First one is a row of HY, of HI, of V empty set is equal to lambda I V empty set. Then row of HI of V I sub 1 I sub k is equal to the highest weight, the ith coordinate, minus, let's see if I write this. So let's put it like this. Sum of j equals 1 up to k of a ij comma I, where these a, ij are simply the coefficients of the Cartan matrix, v I1 up to ik. Next, the row of fi takes v I1 to ik into v I1 up to ik. Row of vi takes v empty set to 0. And finally, row of ei takes v I1 up to ik into, I'm going to write it here because it's a little long, delta of I1, row of hi, plus row of fi1, row of ei, everything multiplied by vi2 ik. Here delta is simply the Kronecker delta, that is equal to 1 if the indices are the same and 0 if the indices are different. So I know these are a lot of equations, but simply they are explaining how this canonical system of generators act on the vectors v I1 up to ik, which is what we need because the canonical system generates G as an algebra. Okay? Finally, remember that positive roots are a sum of simple roots. Here what we have is that weights of a representation are given by taking the highest weight and removing positive roots. That is, that any element of the weight system for the irreducible decomposition is of the form lambda equals the highest weight minus a sum of simple roots, alpha I1 minus alpha ik. Okay, now I have 15 more minutes. I'm just going to make a small comment on on tensor products, and then we are going to be done with the chapter. So simply we're going to define the tensor product of representations. Tensor products. So we're going to stay in the complex semi-simple case because I still want to talk about highest weights, but the construction is general. So let G1 and G2 are complex semi-simple algebras. And we're going to assume that there is for each I a representation of the GI. So we have two representations. Representations rho 1 from G1 to GL of some V1, and rho 2 that comes from G2 up to GL of some V2. So we're going to define the tensor product of these two representations. Define the tensor product rho 1 times rho 2. That is going to be defined in the direct sum of G1 and G2 into the tensor product of the spaces Vi. And the definition for the tensor product representation is that rho of a pair xy over a generator of the form V1 tensor V2 is equal to rho 1 of x over V1 tensor V2 plus V1 tensor rho 2 of y acting on V2. And you extend by linearity. So it turns out that in the case that each of the representations is irreducible, then the tensor product is also irreducible. So, fact, if rho 1 and rho 2 are irreducible, then its tensor product, rho 1 tensor rho 2, is irreducible. And who is the highest weight for this representation? I'm running out of chalk. So choose. So remember that we had to choose torals of algebras. In order to define so maximal torals of algebras, in order to define a notion of roots. So with respect to this, with respect to the sum of these torals of algebras, which is again a torals of algebra of G1 plus G2, the highest weight of rho 1 tensor rho 2 relative to T1 plus T2 is simply lambda 1 comma lambda 2. Here we are using simply that the sum of the duals is the dual of the sum, so this equation makes sense. And finally, these are the only irreducible representations of a direct sum. Any reducible representation of G1 plus G2 is obtained by tensoring irreducible representations. Is equivalent to the tensor product of irreducible representations. Of G1. So to summarize, if we know the irreducible representations of each of the summands, we know all of the irreducible representations of the tensor product. So this is the end of the chapter on my part. So there's nothing much that I can say. In the next lecture, Alberto is going to start with the next chapter of complexification. So nothing more. Simply thank you for coming to these lectures.